Hello and welcome to IGB381 Real-Time Rendering Techniques Lecture 2. And I'm your exciting host, Ross Brown. Today we're going to cover a number of factors. So the CG language, some revision of transforms, and viewing transforms as well. So today, in the light of the way the degree is now run, this is going to be a little bit boring, but I think it might be useful to refresh. I ummed and ahed about it and I thought, stuff it. I'll just give this quick brushing of transforms and camera viewing just to remind people of some of the details if they're not so confident in that space. A lot of you will be. Well, this is a video, so thanks to the fact I'm broadcasting, you can just rifle through it if you find this utterly boring. But the thing that we're lacking last week in the tutorial were some details about shader languages and so forth. So now I'm going to give you some of those details that will help you go, let's see how you do transforms and matrices. And then there's some more details about the CG language in detail. And then at the end, I'll do a quick sort of summary of a third-person camera setup with an arbitrary material. That will enable you to sort of get yourself into the assignment, which I'm going to put CRAs and update them to this year. Not much of a change. If you look on the Subversion server, they are what you're going to do, but I'm just going to modify them slightly just to suit this year and a few other things that I've got to keep in mind. So, some of these origins. I always like to talk about history. Why? Because you understand tradition, you understand how to innovate forward correctly. And the fact is that this stuff came from Pixar. So shader languages had their origins from a paper in 1984 by Cook and Torrance. They also have a few algorithms named after them from Pixar. I believe Cook and Torrance were also given, I might be corrected, were given a Technical Academy Award by the Academy of Film Sciences on their work generating the technology for computer graphics. So you are the direct inheritor. Yes, you inherit all of this tradition in what you're doing in games with these shader languages. And I think that's important to recognize, because if you actually flick through a RenderMan setup, it's a cinematic shader. And it's just an interesting excursion to look at how cut down real-time shaders are compared to the architectures used in RenderMan. I did my PhD in RenderMan, so I'm a bit of a fan of it. And RenderMan, of course, is the system that Pixar use now to generate all their movies. And so everything from Toy Story onwards to Finding Nemo, as we see there, they're all done with these cinematic rendering systems which use a shader language, a much more sophisticated shader language. And that's where this tradition or this work has come from. So, some current languages. Heck, you can build your own if you like. I actually know a guy, Andy Sorensen. He built, I think, his own language, Lisp-like language for GPUs to run some of his simulation code on the cube. So if you go to the cube, which is basically that way, you should see that in there is the physics simulator. And he wrote his own language, I believe, build his own sort of compiler on top of GPU assembly. Impressive work. But for us mere mortals, there are a number of languages available that you can play with, covering sort of both areas, such as GPU. So you got NVIDIA CUDA, which you'll hear of, and Kronos OpenCL. That was Apple. That's now actually an open standard. And the common languages used in computer graphics, not Vulkan and Metal notwithstanding, I think they still use these. I haven't played with them. CG, which is an NVIDIA product, and actually I'm going to edit that page because that's always rendered with a small name for some silly reason. And that works in OpenGL and DirectX. Then there's GLSL, which was OpenGL 2.0 onwards. So that works only with OpenGL. You may have played around with that in your time, or if you did some older units at QUT a few years ago, that's what we used to use for our first rendering units. And also there's HLSL, which is actually a subset of CG, but I think that's probably changed because HLSL sort of bifurcated. Microsoft and NVIDIA, there's that mistake again, worked on this for quite a while and then went their own way, and what are we up to now? DirectX 12, I think. And of course, as I said, like Andy Sorensen, you could always do things directly in GPU assembler. If you wish to, have a look at the compiled shaders in Unity for some insight. This is just a handy thing to keep in mind. You have a look in the inspector in Unity and you can see the compiled code. And then you start to understand that this is not magic, it's just another language. CG is compiled, turned into machine code, uploaded to the GPU and rendered. Yeah, voila. So, we'll be using CG because this is the default used by Unity 3D. So it's easy, comes with Unity, works on both platforms. You'll notice sometimes there will be the odd demo that will come down, and when you try and incorporate it into your Windows box, you'll see you need to change the target architecture from being on a Mac. I'm actually doing this movie on a Mac. I'm going to do the demo on a Mac because of course Unity is cross-platform, so they chose a shader language which was cross-platform by nature, and probably they could deconstruct it and re-engineer it for their own purposes, which is what they've done. So there is a language reference available. Oddly enough, it's not supported by NVIDIA anymore. So they created it and they have moved on. And then Unity picked it up. And then someone sits there thinking to oneself, why did Unity take up that language? I don't know. So in the end, it's actually a historical question I should find out. Maybe I should go to Unity and ask them. But anyway, I also used to use CG way back in 2003 when I started this unit with the GeForce 4 TIs that I told you about. It was new then. In fact, I think I can go and get the textbook now. There you go. A bit of history for you. That there is the textbook I used to use for this unit about 15 years ago, and it's still valid. Who says that things don't stay the same? But as you can see here, the CG in Unity is actually has some additions called Shader Lab, and I mean you can go quite deep into that. There are a lot of extensions, there are a lot of sort of predefined macros that are really handy and make your life easy. They make my life hell because of course every year Unity decides, oh, let's play with the model view projection matrix and how that's defined. And every year it's the error that I've got to fix. So apart from that caveat, Shader Lab's very handy. It gives you some nice little tools to play with. You'll see me using some of them for this unit because it just saves me having to engineer stuff myself, so I can use some of those implementations. Now I know academia should be nice and theoretical and implementation free in computer science, but I think this is just useful because it provides some just handy little macros. So that's why I use Unity and CG. So, like any, basically this is a third generation language. It's not object oriented. That's a cut down version of C++ for graphics, C for graphics. It has a number of scalar data types. These are things you've seen before, they're very C-like. So there's bool, true, false. There's int, unsigned, which is a 32-bit signed or unsigned integer. There's a fixed precision number with at least 10 bits of fixed precision. There's a half type, which is a 16-bit floating point value. This now maps apparently to 32-bit anyway, I believe, so it's probably redundant, at least in HLSL, and probably the same in CG. So you are probably going to just use bool, int, or float. And they are the same as you've learned in C# and in C++ and in C. So it's not really particularly hard here. It is interesting though, for those, again, this is a historical thing. When I did my computer graphics years ago, I used to have to use fixed precision because it was just a pain in the ass to implement floats. Floats were costly, and so what you would do was you would use lots of left and right shifting to do, say, about 7 bits of precision on top of a 32-bit int, and that would sort of mimic a fixed precision float. So this is one of those things that just, yeah, it's funny to see this stuff still hangs around. A fixed precision is very effective. And if I may warble on, hey, I can, I'm not under a timetable anymore, this is a podcast. What's interesting about this is then that because it's more efficient, you just see that turning up in shaders. And so at some stage you will find, if you end up in shader town as your employment, that you will be playing with these things because you'll be sitting there going, oh God, I need about 0.1 of a frame extra in time on my rendering loop because we have to fit in some more AI in the game. You're writing an engine, this is the sort of stuff that you have to keep in mind. So sometimes it's handy to know the old methods because they still hold. It's just they work at a higher resolution and they have a bit of hardware assistance these days. Something to keep in mind. If you want to check that out, actually, some of you will be aware of the demo scene. There's some classic demos out there that start to use these concepts. You know, cosine, sine tables, all sorts of lookup tables to make things go faster. Anyway, moving right along. This is the extra part, or the sort of the data typing in CG that you need to learn for this year that is different and might be different to a lot of the languages you have learned so far. I have an interesting church in this unit, so some of you are stronger, much stronger in software technology than others, but I don't think many of you will come across vector data types as a native data type in a language. And CG has them because it is built upon a GPU, and a GPU as its basis is a vectorized processor, so therefore the types are vectorized. You have here, float, the classic of course, is the float and various versions of that. So here we have a float 3, which that's a vector defining a light position or a light direction. Or you can have a single float. So you just place this suffix here onto the base type and suddenly you have a vector. Here the same vector is created by just defining it as an array. But I believe if you look at the compiler, it's going to put that straight into a vectorized, probably a 4-element vectorized floating point value, depending upon the optimizations and so forth. You can do this for all the base types. So if you want to, you can create a vector of bools. Nothing to stop you doing that. And indeed, you can, again, like any other language with arrays, you can define a vector using the array setup that you've seen with C# and C++ and so forth. And this can be done for each of the scalar data types. And what actually I believe happens is the compiler compiles it down to just all floats, all vectorized floats, so that the hardware does not have to do any playing around with whatsoever and is able to blast through the scene in such a manner. But it'll be good to go that deep one day. Maybe in the masters. Now, HLR, why did I do that? There's all these little errors that come up as you do, and you think, oh, I should fix that, and you never do. Well, now that I'm actually running a lecture with the editor open, I'll just change them in front of you. So CG has vector access in a number of manners. So you can, once you've initialized, so again, you can use the curly braces to initialize a vector this manner. You can then access a value, so a scalar from the vector, by just using square brackets and the 0 indice. So it starts from 0, like C. It's not like Pascal, which starts from 1. Also, you can get the first value because if it's a float 4, it's got a number of elements, X, Y, Z, W. So you can access them directly like a class or a record. This comes in later as quite important. Also, you can, in one instruction, copy from one vector type to another. So here we have a float 2 value, which is being copied X and Y from the vector that I've defined up here. This is this SIMD that I talk about. So those of you who've done hardware architectures or software engineers who cross this, that's fine. But just to understand that the GPU is strongly a SIMD architecture. Single instruction, multiple data. So that means a single instruction can operate on multiple data elements, and that's what's happening here. The assignment operator can work on two elements at once. Keep this in mind, you will see it all the time. And here we have here as well, we've taken three elements out of it. So that means that basically if you have a float 4 there, you can make that equal to, that's not pot, I found another error, I love this. The position can be copied across as three values as a subset, or logically you can just do the whole lot at once and go float 4 value is equal to position, and or copy them all over in one operation. Damn, that automatic capitalization. So that means you can copy across in one operation. So these are all SIMD operations. Multiple data, but a single instruction is used. Note, we can also use XYZW or .RGBA in any of these operations. So oddly enough, I can process a vector, which is representing a light vector, with RGB accessors on the class. So those elements can be used with XYZW, but there are rules about mixing them. You can't mix them into one reference, which I get to, I believe, in the next slide. So, because this vectoring or vectorization is being implemented on the GPU, it enables you to do lots of fancy stuff with these vectors. And one of these things is swizzling, which I believe refers to the concept of holding a martini with a swizzle stick and moving elements of the martini around. Anyway, I find IT people's naming concepts a bit odd. Hadoop, for goodness sake. Anyway, here with vector swizzling, we have the ability to copy any source register component to any temporary register component. So before the instruction runs, the data in the source register is copied to a temporary register and then put into its final location. That means you can switch them. And we see it here. We've got a vector that I've declared, a float 4, all well and good, just like I've done on the previous slide here. But note that I've accessed the elements in a different order. I've put the Y first. So remember these SIMD operations, we can operate on it multiple elements at once, and that means I can do them in any order. I can swizzle, mix. And so that means that vector 2 ends up within its first element, -2. And its second element will be the first element of vector 1, because I've swizzled. Again, something you probably have not seen in a language. I don't know of any other language that does this, so it'd be interesting to find out. But for GPUs, this is something handy and quite often used. If you want to do projections or if you want to switch axes and so forth, these sort of operations are handy because they just do it at once, the GPU supports it, and you're easily able to get it done. In addition, of course, you can extract a scalar, so that's a form of swizzling. But you can also copy the elements. So you can take the element X and make 3 copies of it and put it in a vector over here. So as you can see, the result for vector 3 is a multiple copy of the scalar. So it's just because there's no other element, you can access a scalar with an X, and we can just go, stuff, and I'm going to put 3 copies of that scalar into this vector. And so the vector is initialized in that manner. So we go through a few exercises on this in the tutorial, just to show you the theory of how to do this. The key thing being that it enables you to understand that you can play with this a bit, and you will see this in shaders. So if you download, somebody's written a shader, you go, oh, I need something that does a particular effect. You have a look at the shader and you might find some of these strange swizzling operations. So keep this in mind. Eventually your brain will wrap itself around it and get it. You just have to keep these fundamental elements in your head. Then there's the vector right masks. So you can swizzle and right mask. So this simply controls how many components are written from the assignment, or how they can be swizzled as well. So we can see here you can get elements of them and switch them around. It's all a bit weird. So for these examples, we've got a couple of vectors, vector 3, vector 1, 4 element vectors. And then what I can say is that, or I'll assign vector 3 to vector 1, but I'm only going to write to x and w. The rest are going to be left alone. So that means that vector 1 only gets its first element and its fourth element written to. The middle two are ignored in that operation. Again, something very handy for linear algebra. And again here, I think I just do another example where I assign vector 3 to the same vector, and I've written only its y value with what's in vector 3. So the negative 2 comes through and everything else is left the same. Just a couple of trivial examples, but you'll see that happens as well. So get used to it, that when you see an assignment, what that means is these elements of vector 1 are the only ones affected by the assignment from this vector. Once you get that done, you should be in good shape. Some right mask caveats, or some swizzling caveats, and so forth and so on. Assignments cannot be to the same component more than once. So you can't write to x, x. It doesn't make sense. It made sense in the swizzle because you're saying make a copy of this. All right, I'll make 3 copies of x. Here, you're saying I only want to write to x, and I only want to write to x. That's a tautology, logically inconsistent, and therefore isn't allowed in the semantics of the language. So in this case, that's just illegal. You'll find that should generate a syntax error for your shader. And the other one too is if you mix up the namespaces. So remember I said we could have been doing this with IGB381. In this example here, that's fine, but you can't, because we're going to make copies of things and move them around, but here, X and G, not allowed. Just can't mix X and G, bad news. So that will push out a syntax error as well. Then there's storage classes. So the variables inside your shader are not are accessible to external entities or threads or drivers on the system, and there's some various sort of storage classes you can assign to them. So if you have a variable called variable, if you say it's extern, that can be set by external scripts, but it can't be read back by scripts. So your C# scripts shouldn't be able to read back an extern declared variable in your shader. A const declared shader, const declared variable, yep, you can set it by the external scripts, but it can't be modified by the shader itself. And I think from memory you get a syntax error if you try to modify consts. It spits the dummy, like you find in any, like C# or C++ will do that. And last but not least, a static variable cannot be set by external scripts. So you'll discover all these things are quite useful, and in addition, the static variable, while it can't be set by external scripts, means that any global that is inside the shader can be used by the vertex and pixel shader, as one student discovered last week. Casting. So as with most of the languages like C, C++, it shows its heritage in that you can promote or demote variables from various classes or types. So here we see that it's basically cast what is a scalar to a vector. That operation is performed and promoted this and said, yep, I'm going to make now a float 4 vector. Boom. And this just saves you a bit of code. Okay, so you'll see that quite often, that things such as the vectors or matrices, they can just be assigned to be null or null if you put the value in there, and it promotes it to the class float 4 by 4. But you have to watch the types involved. So float 4 and then a float, and so we have this position here times the displacement, and what happens is that this will actually demote this down to a scalar. So that may be good or that may be bad, but in this case all that will happen is that the first element will be this won't be promoted to float 4, this is going to demote this value down to a scalar and then plonk it in the scalar here. So if you want to be a language freak, these are the things that you need to be aware of in this definition. So that's the semantics of these operations. Keep it in mind, casting in C, C++ is always a bit of a pain. I find it even more difficult than C#, or just a bit harder to keep track of. Gone with days in Koenig and Ritchie C where it didn't matter what type, you could play around with things rather easily. But keep this in mind, that if you start to cast your variables upon the waters, they may come back to you and bite you. What am I doing? Ooh. Okay, so uniform parameters are parameters to the vertex shaders, and they're delivered to them by constant registers. They start with the same value for each instance of the shader. So the idea is that you remember when you're rendering your triangle, it's generating bucket-loads of pixels. And so some of those values will change across the scene because there's just different values coming in for, say, a particular triangle has 3 vertices, or you might be streaming in a mesh and that entire mesh has varying values. But if it's uniform, it simply means for that instance of the shader being called on a triangle, you will get the same value coming in. And so something like a worldview projection matrix would be declared as uniform inside the vertex structure, so to speak. So you don't need to mark that with a semantic. So if you notice here, for instance, this is a vertex shader. It's going to put out the system value position, as I talked about a little last week. I'll just sort of hit on that as a vector. So the transformed vertices that come in, but the matrix, this matrix we're passing in, we're saying, oh, I'm going to project it this way. We're passing that in. It has no semantic attached to it. There is no colon SV position or no colon tech cohort or colon color. It's just a variable. It's a matrix, and you can do with it what you wish. So there's 2 methods of specifying uniform parameters. You can declare globally as uniform, or you declare a uniform value inside your inputs. So if it's declared globally, like v orbit, it's a vector, an orbit value. If you put that as global to your shader, then that's a uniform parameter for the whole shader. But you've got to make it static so that the whole thing will be accessible by all the shader functions, or it goes out of scope. But in this case, we use the term uniform when we pass it in to the vertex shader. So there's a keyword, or you declare it as global. Often I just do them as global if they're uniform variables, sort of makes sense. Varying parameters are parameters which vary for each instance of the shader. So the shader may be called thousands of times across the screen, and in this case, after these variables, these varying parameters, are streamed to them. So they are the things such as the mesh vertices. All the mesh vertices come through as varying parameters. So you might call the shader thousands of times across the screen, and it gets different parts of the mesh given to it every time it's called. And so what happens is that these use the semantics that I talk about in a minute, and what the semantics enable you to do is to line up the parts of the mesh with the variables coming through into the vertex shaders, as I've sort of shown you in the first tutorial, the first practical part. And that links these parameters to just registers that line up on the graphics card. So there's a register that gets loaded with a pointer to the vertex, and that address gets passed over to your vertex shader. And so those registers are hard coded on the GPU, and you put a semantic on them, and then everybody knows where everything is. Otherwise, it's just sitting in memory space, and your vertex shader goes, so where is that variable? Using the semantic, these varying parameters that I'm talking about here get linked appropriately to your vertex and pixel shaders. And they also allow the vertex shader and the pixel shader to talk to each other. The semantics allow those varying streams of data to line up with each other. So that's important. So these semantics that we use to define these varying variables and make them make sense are things such as the position. So a vertex can come in with a position, its position in three-dimensional space, X, Y, Z. It comes in with a color, so you can add a color. So a mesh can color each vertex. So it's not necessarily, because you're probably so used to just using textures, you just, what's that? A vertex can have a color associated with it, and you can change that color. So you can have just a mesh that is colored in a raw manner without a vertex, without a texture. And so you can specify a color semantic, and they have a number attached to them, by the way. So each one of them, n, depends on the hardware. So there will be n number of vertice streams that can be handed to a vertex shader. So the old cards might have 4. The new cards might have 256 streams. I mean, I haven't looked up the numbers. They're hard encoded in the headers for things such as Direct3D and GL, OpenGL. So knock yourself out, crack open Shardy, have a look in the headers, and you'll see some definitions for how many streams and vertices can be handed to that one shader. So just something to look at. You then start to understand that this language is a bit sort of bound to the hardware a bit more than other languages you've played with on the CPU. The hardware tends to be fairly invisible, general purpose processor, scatters and gathers, and you just do Turing complete operations on them. Here, not so fast. Because things are so, that was ironic use of the word fast, you can't just roar in and assume just a standard sort of memory space and setting up of variables. Here you've got to tell your system what registers you're using that have been set up on the hardware to accept streams of data, because they just make it a very fast system. Anyway, so you have texture coordinates, which we get to when I talk about textures. You have normals, which you should have covered the concept of that in 283, and also the tangent. You will then create binormals when you get to do normal mapping, and you'll use binormal, normal, tangent spaces for a lot of things in computer graphics to get used to seeing these semantics appearing. And like I said, n denotes how the range goes. Also might want to know, textures can be 3D. You may not have played with 3D textures unless you've done some advanced graphics. I'm going to show you just a simple noise texture. Cody Phillips's favourite word that I say every week at 301, Perlin noise. I cover a bit of that, which is just a stack of 2D textures. That's all it is. Then there's the system value semantics. CG has some special system value semantics, which are aligned mostly with vertex positions. This is because of the geometry shader. I don't get into the geometry shader, I've just run out of room in this unit for stuffing things in. So I just sort of ignore it a fair bit in this unit. However, it rears its ugly head because it has a special semantic, which just simply says, as you stream from your vertex shader out to the geometry shader stage, if you had a geometry shader stage there, you can then align up using these semantics and create lots more points if you wish using the geometry shader. And it starts to make sense, because if the geometry shader starts allocating more vertices, then they've got to align up on the streams. And so there's an internal representation for that, SV. So you'll just see that the shaders, the vertex shader's output position is always an SV position because of the geometry shader. There was a change in language years ago when they didn't have geometry shaders and I was teaching the unit. That didn't exist. You just put out a position. But now, because of this geometry shader, they've added that. It doesn't really have to matter, but keep this in mind if your vertex shader complains about some sort of output semantic. Remember, your position should have SV underscore in front of it for the output parameters of the vertex shader. So here's an example of an input, a set of input variables. They're varying variables, so they've all got the semantics attached. And these you can clump together. I think it's quite convenient actually to put them in a record or a class. Record, that reveals my Pascal days. Sorry, this is the parameters version. I think probably I cover later on, I show some, I've got some structs, some classes. So sorry, this is a function, just to make it clear. And hopefully I haven't confused you there. So the function VS, the vertex shader, has these variables coming in. They're varying, they don't have uniform in front of them. And they've got the semantics attached. So that's the position, text coordinate, the normal, and the tangent. So later on in another lecture, I show how this sort of maps over. I say, if you look inside a file, like a collada file, or even some sort of simple .ply file, just a text file, you'll see how these elements come with those objects you download. Things like FBX files, I think, are a completely binary format, and so therefore you don't get to look inside them. If you look in collada files, I believe it's XML, and you can see the different definitions for the positional vertices on the meshes, the texture coordinates on every vertex, and the normal and the tangent. Suffice to say, these things come in. Most models that you download and find on SketchUp Warehouse and so forth have these. So keep this in mind. Have a look inside the files and you'll see these elements appearing. And these things map to what you see in the file. It's read up by the CPU and streamed across to the GPU. So the vertex shader output semantics. So as I mentioned, there's the system value one. Fog, I think I've ignored fog. I just had to drop it. There is some hardware fogging that can be used. You can spit out a new color from the vertex shader. That can be a lighting color. So you can do lighting in the shader. You can do Guru shading, which I get to, I think, next week when I cover the first sort of more complex shaders to use. And then there's the texture coordinate that comes out as well. So again, the vertex shader, remember, it can transform them. I showed them to you. I just did some color changes. I did some transforms. You got your cylinder rotating around. So now maybe it gets a bit clearer why you had to do things the way you had to in that shader. Again, hardware will constrain the number of these semantics. Probably, I don't know how many textures, probably like 3 textures max you probably load up in any of the things you use in this unit. I don't think you go further than that. Sort of diffuse texture, normal map, and maybe a visibility texture. But of course, if you're doing professional and cinematic style texturing, there's quite a few layers that come through, and you have different texture coordinates to play with them. So that means that you can have multiples of these. Keep that in mind. So the vertex shader output, so here we've got a struct. So instead of having it as a parameter out, we can specify it as a struct. And we're going to spit out the projected vertex and texture coordinate. And you can see that the shader output, we either at least need to put out just a position, because that's going to be rasterized. So once the vertices of the triangle, that's a diamond Ross triangle, get rasterized across the scan lines, they're going to be pumped out to the pixel shader from here. So you at least have to do that. If there's no vertices, there's no content. There's nothing to appear on the screen. So it's only logical. But you can add other things, colors and texture coordinate systems. And if you wish, you can just return a float 4 like we've done here. That's a product of whatever calculations you've done. That's at least. Or, just for variation, you can use the out value, keyword in the function header, and you can spit it out. So that we've got this struct here. You can say, oh, there's an output variable. It's struct vs output, and it's out, and so you set out dot blah 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 projection v this, and then go return out v, and it knows that it's going to pass it out of there. If you wish, you could return instead of a float 4, you could wipe that out here. So once again, because I'm podcasting, I can edit these things. So. And we could just spit out a VS output struct. And then since out V has been declared somewhere as VS output, you spit that out. But anyway, I'll just take that back to what I have, because this is just another variation. You need to just be aware of these variations, because some people will like this as a method for spitting variables out. Okay, now moving to the next, the pixel shader. So remember, what comes into the vertex shader gets transformed, kernel is applied, spat out to the pixel shader. And so the pixel shader input is again the system value position. They just line up, makes sense. And a color and a texture coordinate. And we'll see there that this is just an example pixel shader. And what's coming in, well, there's a stream of system value positions and a stream of texture coordinates. And lo and behold, the pixel shader spits out a color. Bang. And that's the end of the pipeline. So once that color is in the memory for the frame buffer, then your graphics card just simply has a chip that reads that out and generates LCD colors on the screen in front of you, which you are now watching. Years ago it was a CRT. Years before that it used to be vectorized graphics. Everything was drawn by a vectorized beam. But anyway, now it's all LCD or variations of that, and that's what you see in front of you. And yes, so basically in CG, the only thing that comes out is a color. HLS allowed a depth value to come out, but in Unity, you read the depth value as a texture, and you can generate depth textures. So they sort of control that with their own texturing framework over the top, and that seems to be one of the changes. I haven't played with it, but I don't believe Unity will let you put out a depth value in the pixel shader. You could put your depth value out as an encoded color. Have a look at the shadow mapping demo and you'll see that's what we actually do. So it gets a bit complex. So as we can see here, our pixel shader spits out a color. So if we wanted to, we can put it in a struct. It almost seems silly, but you can do that and spit it out. Or we can declare the semantic for the shader there and just go colon color. Control flow. third generation languages all require this, and this is a necessary thing. So, but the control flow is the same as C++. So for loops are the same. For a while there, you couldn't actually. So I think when I first started, you couldn't even put a for loop in a pixel shader. Wouldn't let you. Not enough instructions. I think you would have 256 instructions available to you for the pixel shader. Now you just don't care. Anyway, so yes, it allows for fully variable looping. So I remember I added the while and the do while and a fully compared dynamic if to the number of things we could do in shaders. Years ago, you couldn't do that. So ifs, for instance, were only fixed. You could compare a value with a fixed value. You would just say, this is the number 16. Take it or leave it. Now, doesn't matter. Pixel shaders are so sophisticated, the GPUs are so powerful that they can predict the branching and control the load on the cores quite capably. Therefore, as you can see, all these constructs are the same, and they match completely with what the semantics you will learn in your other C#, C++ lessons. So it's all the same. Nothing to worry about. Nothing to see here. Move along. Intrinsic functions. Intrinsic functions are just very efficient, encoded, system encoded functions that you can use for various mathematics. So a lot of the linear algebra you've done, it's already there for you. Some quite handy ones as well. So things such as the maths intrinsics incorporates things such as a cos, a tan, a sine, and sine, cos, and tan, of course. So they're all there. Converting things from one number space to another takes from degrees to radians for the trig functions. The one we learnt last week, multiplying two matrices. So that's been vectorized. So you might have implemented it in 283 in an unvectored form. Gene Lang will have covered how you do a matrix multiply and then a multiply of a vertex. This has been efficiently set up for you to do vectorized multiplying. Then there's the cross product of two vectors, the reflection of a vector around another, so reflection of an n around the other vector I, or a refraction around, there's a capitalization again, a refraction of I around n around a value with a refraction value included, eta. So when we get to refraction and we talk about creating glass objects, that function comes in. There's tons of them. Look at the Unity CG doc for the rest. But generally, if you see a function in the math, probably being implemented. The basic operations, binary or n-ary operations, are implemented for you. You can sit there and you can use it. So, and I don't expect you to recreate them. So just use them. They're more efficiently developed than what you will write. So the hash pragma section that I mentioned. So this is where you typically set up the function names. So you define what will be used as the vertex shader and the pixel shader. So on the trivial demo, it's normal mapping, and pixel shader was normal mapping. So you specify that at the top of the setup. So that's part of the, I think it's the Shader Lab components. And then there's the hardware profile. So I've already mentioned this in the tutorials. So this is handy because every year you get new GPUs and drivers, and your experience with CPUs is like, it's a processor, Turing complete. It does what you need to do. If it's big enough, I guess you could simulate the universe on it. The GPU, that's a different animal, and especially as Shader 3 is sort of broadly cross-platform, but there are other numbers. You can go up in complexity to Shader 5. I haven't pushed it. I should. This is one of those things where it's like read the fancy manual, Ross. The shader numbers will go to, I think, Shader 6 by now. Maybe they're going to Shader 7. The hardware keeps changing, they introduce new features, and they update the shader languages. So this is where you might have a bit of code in your game that says, oh, I'm on one of these old units, and so I will keep my shaders to shader 3. Oh, I'm on one of the newest GPUs, so I bump it up to shader 6. I mean, this gets to sort of business decisions. As a game studio, you decide what is the hardware platform you're going to implement on and its capacity. So you have to do that. That's your decision. And once you decide that, you choose a shader level, and then you stick to it. And it just means that there's some sort of control about the complexity of the driver, the complexity of your shaders, and also means you can sort of just vary your graphics to the hardware that you're given. Okay, and then Shader Lab states that enable you to modify the graphics pipeline in the effects files. So one of the classics that you're going to use is blending operations. So you'll see in a lot of the blending operations that here's just the classic. The blend function is the source alpha 1 minus source alpha for the destination, and that blends a component alpha of the source plus 1 minus that component of the other destination. Boom, it goes together and you get a blended color appearing in the frame buffer. So some of this stuff actually also, when we used to do it with DirectX, you can call this from DirectX. These things are also in the C# functions you can call in the scripts you write in your game. So things like blend states, I believe you can actually set up using scripts in C#. And you'll notice that. I can't teach all of it, I haven't got the time. So some of these elements will also be present in C#. You can have a look at it, and if you think it's appropriate, you can just call it from the script in C#. Or you set it up in the shader, so that when this shader runs, it will do blending this way. Just a decision you make as a software engineer according to how your system is supposed to work. It's also handy if you want to tweak some variables. You don't have to recompile the code. You can just rerun the shaders. Now, this bit is a revision of 283 components. So I'm just going to rifle through this because most people should know this. And I just thought, well, I'll leave it in there because it just sort of makes a more gentle introduction to the unit. So starting from scratch with geometric transformation. So the rationale here is that transformations are basic tools you use to build and move objects and images within a computer graphics or a synthetic environment. Might be 2D, might be 3D. So the transformations that you get, translation, so moving things around without rotating or scaling, and then you have a scaling, which is make the thing big but not move it. And then rotation, which is maybe a rotation around a particular fundamental axis. I've just twisted the object there, but anyway, you rotate it around the object, you rotate the object around, or you may choose a point of rotation and have the object move around it. And then we could do reflection and shearing. I cover reflection in a certain manner later on in the unit, not as a fundamental transform. So that comes along. I don't do shearing, I don't think, in this lecture, but I cover projection. So that's also a useful one that's coming up. So you can just be aware of how projection fits into the whole transform pipeline you use in your computer graphics system. And they appear, all of these appear and can be manipulated, as I showed you last week with the hardware, the practical session, inside the pixel or vertex shaders. They allow you to do these transforms. Typically it's done in the vertex shader. So the aim will be So the idea is it allows you to move objects, resize them, modify their orientation, reshape, distort, and project those 3D scenes to 2D images so that you get a 2D image on the screen in front of you. Interestingly enough, I guess, one day they'll invent a hologram system. And so the projection, to a certain extent, becomes meaningless because it will just sit in 3D in front of you and you won't have to project the objects to appear. Now, there are some systems out there for this, and so the projection, yeah, it's interesting. They sort of have to, some of them have to pseudo-project in order to generate the 3D-ness by spinning discs that are flat. So they project onto that and change the projection as they move the disc around. They spin it very fast, and the 3D object appears in front of you due to not ocular fusion, I guess, visual fusion. So there's a couple of transform stages that you need to be aware of, and you'll see that appearing in the matrices you generate. There's a model to world transform that arranges objects in the scene. So you have defined your object in your CAD package at some sort of origin, and you go, right, that object, might be a car, appears at this location here in the scene. It's your model to world transform. And that often includes dynamic things such as the wheels in the car rolling around. The view transform is then, right, that's its position in the world, and then we have a camera that wants to look at that. And so as we get to, we actually transform the objects so that they match the z-axis, looking along the positive element of it, the positive component of it. And so that means that camera transforms change the world to match your monitor. And these are performed in the vertex shader. You can do some transforms in the pixel shader too if you want to distort things, take texture coordinates and muck around with them. But anyway, once you have sort of distorted and moved your objects around, they get rasterized and blasted onto the screen in that final stage, the pixel shader, typically. So the vertex shader is where these transforms will turn up. I have a briefing soon. So the pipeline, the transforms that you are going to deal with, and you will deal with these, I base it on Direct3D because most of you are doing Direct3D instead of OpenGL. So in today's lecture, I'm just going to get these three parts done. It's going to be that the model space, the model is defined at some location, and then a world matrix is applied, and then a view matrix is applied, and at that point the world is oriented to a canonical z-axis so that it's ready to be projected onto a 2D screen such as the one you're staring at while doing this, looking at this video. There are other stages coming. There's a projection, and then there's a clip space. Maybe you noticed you'll see it in the tutorials, you notice that the Unity gives you a projector clip space. That's sort of those three variables put together, world, view, projection. And then in clipping space, there's a viewport transform. So that's taking the canonical space and stretching it out and translating it appropriately to match your screen. And then finally, you divide by W, you then got a pixel, and you fill that pixel with color. That's the final thing that the pixel shader does. So it's dealing with viewport transform fragments that are already on the screen, and then it fills them with color in screen space. So the general representation of transformations, so we have a point, you multiply it by a matrix to give you P transformed, P colon, not P colon, P apostrophe. And if you take those and multiply through as per your previous theory, so X times A plus X times C, so it's row by column, and then in this case, X times B plus Y times D, and so your final transform point P is AX plus CY, BX plus DY. So the right side also represents a point in the xy plane. So symbolically, to transform the point, it is P, which is xy, and it is multiplied by some sort of matrix F, where F is equal to A, B, C, D. This is for 2D points. It's not homogeneous. And so if you want to implement translates, you can use a 2 by 2 matrix to move points around on the xy plane. All good. That's in 2D. There's a number of transformations that you should be aware of. And the first transform is the identity transformation. So that is simply that the point is transformed to the same position. So as we can see here, if you run through, if F is equal to the identity matrix with the leading diagonal equal to 1, then the points, the final transform point, P transform, is equal to P. So P prime ends up being the same value. And so that means an identity transform leaves the coordinates unchanged. So it's a good initial point for your transformation matrix to be. If it was zeros, then your scene disappears in puff of smoke. So this is where, if you set your positions of your objects up appropriately, you can make them fit on the screen without any other transforms or projections required. You just drop the Z, and if the values fit well within the viewport transform, they appear. So you can view it with an identity transformation if you need to. Scaling is another factor where, say in the X direction, so we can have a matrix SX with an A factor which scales all the X values, but it leaves the Y values the same. So X values will move across, and Y values will not move up. So this set of points here gets scaled out, in this case 2 times, and that moves the points across. So the matrix form for in the X direction is A0, 0, 1. Straightforward. In the Y direction, we use B down the bottom right corner, and we see there that the points have been scaled up, in this case by 3, because we just choose a number. Excuse me. So you can combine them together. They are independent operations. You can scale in X and Y and end up with a matrix A, B that transforms X and Y and scales them around the origin. So that means if A equals B, it's a uniform scaling, which is sort of most of the things you're going to do. You're just going to make it bigger or smaller, but sometimes you want non-uniform scaling, such as just getting some sort of distorted effect on your shape. So scaling around the origin occurs. So if you have your objects situated around the origin, then the vertices for our 2D triangle here, if multiplied by these transformation matrices, so 2 in X and 3 in Y, we end up with the points expanding out, and so it looks like the object sort of grows around the origin. So note, scaling is about the origin, and therefore if you want your object to scale a certain way, you should translate it to surround the origin, or you leave it there depending upon how it's defined, where you put it in the CAD system or modeling system you used, and then that means it gets transformed back, the scale is applied, and then you put it back into its final place. Then there's rotation around the origin. So we can use polar coordinates for this, where we use the radius and phi, the rotational angle. And so if we want to, using that sort of notation, then we can transform X by cos phi plus theta by R, and we can go Y prime is equal to R sine theta, sorry, phi plus theta, and that will make our point rotate around the origin. So in this case, in 2D, cos phi plus theta, as revision, is equal to cos phi times cos theta minus sine phi times sine theta. And sine phi plus theta is equal to sine phi cos theta plus cos phi sine theta. So that means if we write all of that out, x prime and y prime, our transform points, we can then place them into a 2D matrix like this. So rotating around the origin theta, so adding theta to the angle of the position of where it is in space, so it's at phi at this moment in time, and we add theta, comes down to this rotation matrix here in 2D, non-homogeneous. So here's an example of rotation around the origin, original triangle, rotational angle, and then it's mapped out here. So there's the example there on the screen as an image. I'll leave you to do that. This should be just revision. Or we can to think about this slide. I've lost my place. I've been going for an hour and a half. I think my brain starting to fade. Oh, sorry. This shows that we're using the matrix and multiplying row by column with a postfix form. So r theta with a transform. So we see here that in order to get the same effect, if we do, if we switch around the axis, the leading edge axis for the matrix, then as we can see that r -1 has moved up to the top right corner, and we multiply then the points minus 40, 40, 40, 40, 0, minus 40, then we get the same transformation occur, but it's around the other way. And this is how it works in CG. Keep that in mind when you're thinking about the order of your transforms. So in the end, it is that row of the matrix times the column vector, whereas before we had a row vector for the point times the matrix, and it'd be row times column. So when you look in the shaders, you'll see that it tends to be the transform times the point in this order, and this is how it works in CG. So translation can be done as considered as movement without change of orientation. And so in this case, x prime is equal to x plus dx, y plus dy. Cannot be represented as a multiplication of matrices, where t is just a 2 by 2, but of course we get to homogeneous coordinates, which most of you know is coming. But it can be represented as a... Okay, back to the lecture after a snacky poos and some rest and recreation. So, if we're going to transform an entire object, we see that it's pretty simple. Unity in the background is taking the points that make up objects and is applying a transform to all those points, and then we'll re-render them. And in the case of the transforms we use, because we don't, if you have a geometry shader, topology changes. In this case, topology doesn't change. The meshes stay the same. They may even use an affine transformation all the time, but whatever. The points will be transformed and the object re-rendered by the Unity engine. So the present formulation, of course, we can represent all the transformations, that's fine, but translation cannot be obtained through multiplication. Nice if it could. So that last little sucker there is a bit of a problem, because that means we can't then multiply all the transforms together. Enter homogeneous coordinate systems. And we know this We embed the xy plane in a 3D space, x, y, w, at w not equal to 0. Or x, y, w is equal to x over w, y over w, 1. So now a point xy is described by the vector xy, 1. And direction is described by transform dx, dy, 0. And these homogeneous transformations allow us to therefore turn the translate into a matrix multiplication operation, and therefore can use them in a concatenated series of transforms. So the transforms now become these forms, which are 3 by 3 matrices. Cover them in 283. So you'll see scaling A and B across the leading diagonal with a 1 added to our homogeneous coordinates. Translation can now be inserted at dx, dy across the leading coordinates there. And rotation around what is effectively, I guess, the z-axis, because we have the x and y, where rotation on the 2D plane is cos theta and so forth inside our matrix 3 by 3 with the extra dimension added, giving us homogeneous coordinates. So that means, in general, we generate a sequence of transformations. So that means that you're just going to have to get used to, in the vertex shader, playing with these points and these transforms and multiplying them together to get the final transform you need of the scene. And in fact, if you go through it in more detail, these transforms are being applied in what is effectively, I believe, a child sibling tree inside the unity system in order to transform the points effectively. So you have inheritance of previous transforms by this multiplying factor. So that's why where you position the object in the tree of the inspector will change the way the transforms come through. Keep this in mind. So some inverse transformations. We have therefore the inverse translate back to the original point by minus dx dy. I think that's fine. And if you multiply the two together, you end up with identity. Straightforward stuff. The same here with r theta and r minus theta, or scale AB, or scale by 1 over A, 1 over B. Then you multiply the two together, you get identity. And then scaling and rotating around an arbitrary point. The process comprises of 3 tasks. You translate the points to the origin, so that the point that you're rotating around, in this case P, X, C, Y, C, is at the origin, together with the object to be transformed, so they're all translated back. You scale and rotate around the origin, and then translate via that original point P back to its original position, and that means it's been transformed around the origin appropriately. If you were to grab the slides, there's an animation here that shows it quite clearly. I'll leave that to you. I'm running this in editor mode because it's convenient for me when I'm podcasting. Oh, I've got a meeting with my master's student. Very good. So, moving on. Combination examples, scaling and rotation around the origin. I think there's another animation in here somewhere. So to scale the indicator figure non-uniformly by a factor of 2 on x and 1 on y about the origin, and then subsequently rotate it through an angle of minus 45 degrees again about the origin. So determine the scaling matrices. Yep, 2 there, 1 there, blah. Then rotate by minus 45, that's all good. So if we combine the two together, we end up with a stretched parallelepiped. Think about that one, trapezoid. In X, and then it's rotated around the origin, so we end up with the object down there. So as a single transform, just multiply the two together. So put them together and you will end up with a transform matrix that does this in one hit. So it's scale to 1, rotate minus 45 for the transposed points, the transposed matrix and the transposed points, PT t. Excuse me. So once you've done that, you've got the principle for how all these transforms are put together. However, care needs to be taken to the order of the operations. And this will matter to you when you're playing around inside the vertex shader if you multiply them in the wrong order. So at this stage, CG acts like this. It's the matrix times the points. That's the order you see it in. So you do it in that order from left to right. The first one, followed by the next one, followed by the next one, followed by the transform on the points. So what you don't want to do is get it around the wrong order. So if you do that, you get a different transform. So if you scale by 2, 1 and rotate by minus 45, you can rotate by minus 45 and then scale, and you get a very different answer. So note that the whole idea there is, and typically the idea is, 2D and 3D, is the first operation you apply as a scale. Usually it's uniform. So you want it to happen around the origin of the object. Typically objects are defined around an origin, and either you translate that origin to the object space origin, and then you apply a scale. Then you would probably apply a rotate, because usually you don't want to deform the object, you just want to rotate it around its own axis, and then a translate to push it into place. So that's a typical rule. So it's SRT in that order. Then you multiply the point. If you don't do that, you will end up with all sorts of weird and wonderful combinations. Again, keep this in mind, because the matrices in the shaders will inherit what they get from the hierarchy in the inspector in Unity. So in 3D, we're interested in rotating in 3D, so we need to extend our 2D to 3D transforms. So they look very much like 2D. You just add a Z dimension, so it ends up being a 4 by 4. For translation, dx, dy, dz. Rotation, well, what is that rotation about? So that's what we have to think about. So rotation in 3D is not so simple. Rotation is performed around a coordinate axis. In 2D, of course, it's just the plane of the screen, because plane of the screen, the plane made by the X and the Y coordinate system. And in this case now, we have to rotate in 3D, so we've got 3 coordinates we can base that rotation around. There's just a simple basis: rotation in X, rotation in Y, rotation in Z. Remember, I got you to do this for the first tutorial, just to play around with these concepts as matrices and so forth. So here's the theory, knock yourself out. And I'm not covering quaternions here. Probably should one of these days. We really do need another unit in this degree, don't we? Hint, hint. So let's do a rotation. There's 3 angles around each of the axes, and they're called Euler angles, but they're subject to gimbal lock, which is why quaternions are used, because you can linearly interpolate between the 2 positions much better and avoid the gimbal lock that occurs. So the matrix multiplication is not commutative, and angle combination order is important. So if we want to rotate about an arbitrary axis, so we still want to use Euler angles. In 2D, rotation is performed around the origin. In 3D, rotation is performed around the X, Y, or Z axis. To rotate an arbitrary axis, we need to do 3 specific things: center of the object, vector about which we will rotate, and the angle of rotation. So you need to move the center to the origin and align axis of rotation with coordinate axis. Translate. So to do that, we need to translate the object so the object's center is at the origin, t minus p. That's trivial. Rotate to align vector with z axis, not trivial. Rotate about the z axis, trivial. Rotate to undo alignment, not trivial. And then translate back to the original position. So that just gives you a smattering of the transforms that you've used in this unit. Because my unit's basically about surface representations more than anything else, So those sort of transforms and that sort of stuff was covered in 283. So it's not a big thing in this unit. As long as you get that you have to multiply those matrices together and you understand the basic transforms, you can make your shaders work. More than that is beyond the scope of what I can teach in this unit. So we now quickly go through the camera transforms, because they're made up of the basic transforms. There's nothing new here. Camera is treated as you basically transform the world to match the z-axis that's coming through the bottom corner of your screen into the world, because that ends up being the positive z-axis. So most hardware, DirectX is a left-handed system. So it's from positive x to positive y, z, positive z comes into the screen. This matches the hardware. OpenGL likes the right-handed system, which is more mathematical. So x to y, z comes out of the screen actually. The reason why z goes into the screen is because in DirectX, because traditionally they're closer to the hardware, z is an unsigned int in the z buffer. If it's unsigned, you don't want to deal with the negative. So the logical thing is to have your entire coordinate system just be with a positive z into the screen. So def buffer, unsigned int, lots of precision, or an extra bit of precision that you can use. 32 bits instead of 31 bits, because you don't have to encode the sign. And so that means you have a positive z into the screen. OpenGL, oddly enough, actually implements a switch halfway down the pipeline. It scales in z by -1 and turns itself from a right-handed system into a left-handed system to suit the hardware. I discovered this while I was building my own version of OpenGL. That was just an interesting thing to know. So those transforms now come back to be used as a camera transform and an analogy. You're probably used to playing with cameras a lot. So really the concept of the camera is probably a thing you're used to because you've been building games, getting basics down pat, and that David Conroy would have been giving you all those scripts for IGB100 and the tutors and so forth there. Ginny Lang would have covered that in IGB381. So again, I just cover it here quickly because the interesting thing is that's another transform. You can access that in your vertex shader and you can play with it independently in a shader. So the idea is we need to position and aim a camera in our scene to obtain a desired view. So if, I just like using my mobile phone as the example because it has a camera on the back. So it's like if I want to see the keyboard, then I position the camera looking down. If I want to take a selfie, I put the camera back to me in the position there. And you need to transform me, wouldn't that be fun, to the viewport on your screen in order to see me. So that's the basis of the camera transform. You change the world to match the screen, this thing in front of you. So it means that effectively, if you follow the trace, the camera rotates around and matches the screen here. And doing that, you move the world. So funnily enough, I would end up behind the screen and behind the camera, and you would no longer see me because actually the camera you're seeing me with is right here. Whereas this camera needs to match the bottom corner of the screen, so you can see me sort of moving it down to there. You can do that transform in your head. So it is analogous with a photograph and a camera, and I'm not doing it with an iPhone. I'm doing it with an Android. And the whole idea, therefore, is you need to get that transform right to mimic that. Now, of course, Unity has the camera model exposed to you in this electrifying inspector space. So the position of the camera, the rotation of the camera at any time, position and rotation, the field of view, if it's a projection, a perspective projection, clipping, near and far and Z, a little bit on that, and the viewport. So of course you have your world, which is in object space, in world space, and then camera space, but then that's got to be turned into an image. And the way to do that is via the viewport transform. So the viewport basically says this is how big my window is in Windows or Mac OS X or Linux or the graphics system on the phone. So all these things contain a certain resolution. So the final step, that viewport transform, turns everything into the space that can be turned into pixels, where your pixel shaders start to take over. So your vertex shader handles all these transforms I've talked about. Then after the viewport transform, your triangles end up being rasterized, turned into fragments, and then those fragments, if they're visible, get colored by the pixel shader. Look, I can leave you to look at this video. It's just me playing around with the parameters. You've got a bit of stuff, narrative that I do. Have a look at that. It's the oil drum, the old version normal mapping demo, and I just play around with the camera parameters in it to show you how that changes the model. But I think you're across this pretty strongly. But this is just for those who have come in out of other units, got the maths and not the Unity. So the camera analogy, there are 4 aspects of the viewing process that we need to consider, all of which are implemented in the pipeline. So you set up your tripod and point the camera at the screen. That's the viewing transformation. You arrange the scene of the objects. That's known as the modeling transformation. You select a lens or adjust the zoom. That's the projection transformation, which I'll show, I think it's next week. And then you determine the size of the final photos. Maybe they're enlarged. Maybe they're made smaller and miniature and placed inside a locket close to your heart. Whatever. So the viewport transformation then determines the size of the final image, the number of pixels that it makes up. And all those stages are set up appropriately. Actually, I don't like that order, so I'm going to arrange it on the fly, because we can do the wonders of modern PowerPoint technology. The first thing you do is arrange your scene. You move your objects to where you want them to be. Then you do the viewing transform. MVP, modeling, viewing, projection. The viewport is out of your control because it's done by the hardware, but it is implemented and you can change those parameters in Unity. Camera movement, so the rotation of the camera. Tilt is rotation on the x-axis. Roll is rotation on the z-axis, so I guess if the camera's up like this. Okay, slightly interrupted there by a student coming through, so now back to the camera movement. Let me get context. So, direction and orientation of the camera, so I think I showed you before. That's tilt, pitch. Roll is rotation around, so it all derives from flying planes as well. And yaw is rotation on the vertical y-axis. So all these things you've played around with when you have played with the rotational matrices in your camera transforms. They're available to you in the vertex shaders. You can play with these. And the other ones dealing with position, dollying, which I find amusing, forward and back. Dolly is left to right. What am I saying? X-axis, left to right. Truck, zooming, boom, panning, up or down. So the idea is, of course, you've played with this as well, and these camera motions can be used to simulate the various things you want in the game. Key thing is, you're across this, you've used Unity. The key thing is, all of this comes through into the vertex shader. You have access to that transform in the vertex shader. You can play with it if you wish. There's nothing to stop you creating a camera model inside the shader. Now, I don't do that. I don't make you do that for the game. I just get you to basically transform points according to the view transform handed to you. But we can play with that if we wish. So the camera, graphically, the world and the camera frames are the same. So the default matrix is an identity. That means, effectively, that the middle of your screen, accounting for the viewpoint transform, is the z-axis into your world. And the camera is located at the origin, so it's sitting at 0 and points in the positive Z direction. So that means if you just position your objects vertices in the right spots, they will appear in the correct location for you to play with. So the idea with the viewing transform then is to orient the camera so you can see the scene effectively. So the objects are drawn in world space for easy reference. So the whole idea is you've got multiple spaces. So as we said before with the camera, arrange the scene and the objects. So you do a modeling transform. That's the hierarchy you see in the inspector on the left-hand side. I'll point it out when I run the demo. That things are left in a hierarchy to absorb these transforms and to place things in the world. And then you apply this camera. The camera is a matrix. It just gets applied to the early transforms to put things in the world. And that what that does then is position everything in the world so it appears abstractly behind the screen. So where my hand is going now, behind the screen, is where the objects end up, conceptually, because it's a left-handed system. So the idea is then that to move the world to camera coordinates, so from you've moved your objects into the world and you want it in camera coordinates, you perform a translation that will move the origin of the world's origin to the camera's origin. So imagine your camera's here looking at the world. It's at a position. The first step is you make it the origin, and then there is a rotation applied to each of the axes to make them line up so that your camera location is along the z-axis. At the same time, the objects have had this same transform applied to them, and as I said, it's like they're behind the screen, and so that means that you end up being able to see those objects on the screen in front of you. You turn them into pixels and the world appears. So going back to some of our CG elements, those transforms get implemented as matrices, and they appear to you in CG as a fundamental unit in CG, 2D arrays of values. Now we touched on this in the tutorial, float 4x4s. They're homogeneous coordinates, it's all based upon the theory. So CG allows you to make them from any scalar type, but you're going to basically be playing with floats most of the time. You don't make matrices of booleans. You might, but it's sort of nonsensical. It'd be interesting actually. You might use that in some sort of AI engine, but anyway. Large matrices of booleans, true and false, be just 0 and 1. So they can be theoretically any size, but typically 4x3 or 4x4 are common. And like vectors, you can use array or structure swizzle syntax. So matrix access covers a number of elements. So with the swizzle form, you can see there's an underscore and then a reference to the row and the column. What you should note is there's two forms you can use. Underscore lowercase m, and then from a 0 origin indice, you access the rows and the columns of the matrix. Or you use this underscore and then directly starting from 1, which is probably actually a good question. I think I just swing between these depending upon what I was doing on the day when I was building the demos. I don't know what the preference is. If you're a mathematician, you probably like 1. If you're a computer scientist, you like 0, because you're used to that with memory pointers and indices. I'm not going to prescribe anything. Also, at the same time, you can use array forms to access the matrix elements. So here's a float 2x2 matrix with these random contents. And if, so that value there is a scalar returned from the matrix. So the 0th element is 3. That one there, row 0, column 0. Underscore M00 is is 3 again. It's the same thing. Using the underscore straightforward 1 indice float, it's going to be 5. So it's row 1, column 2, 5. Again, using the array approach, because it starts from 0, so matrix 1, 1 is going to be the bottom right-hand corner, so the value will be 1. And so on as goes. And because of the vector swizzling, we can apply that again here, and we can extract a row from the matrix in one operation. So now we can see there it's underscore 2, 1, underscore 2, 2. So you're getting the second row, 2, 1, and you're putting it in a float 2 vector. Very handy for ripping out the guts of matrices in various linear algebra operations. I can even hear now the mathematicians in the audience getting excited. Especially those that use R. And then finally, down the bottom here, what are we doing? Oh yeah, so this is another way to extract a row. So I guess it's an implicit cast. And it's, this is, sorry, what am I saying? That's incorrect. Strike that from your memory or notes. That just refers to a course using the first indice as the row inside the array, the matrices. So if you don't use the second dimension on a 2-dimensional matrix, you get a row, and you can put that into a vector. And here we're going to get the second row. So it's 2, 1. Boom. So again, you can swizzle these things around. All the same ideas apply as per the vectors. So the modeling transforms that are available inside of the vertex shader. So remember I said, I just wanted to review them because it gives you a context that when you're looking at this stuff, it's like, oh, that's what he's talking about. So when you place objects in the world, remember that was the first step, a transform is recorded in the internal scene graph of Unity. And you may modify that using a C# script to animate objects, change this transform matrix, etc., etc. You can modify it. You do that already. You've built your games. You know how to change the elements in your scene. Instantiate, destroy things, move your character through the world, all that sort of stuff. But in the vertex shader, the object transforms, so when you've got whatever you've modeled in Maya and then whacked it into the world and its position in the hierarchy, the transform it inherits is defined as underscore object to world, float 4x4. Get rid of that spot there, that space there. That is what you have available to you in the vertex shader. Declare globally, you've got it. So you can use it anywhere to perform those transforms. You've got it available. And this is one of the nice things about Shader Lab. This stuff is already set up for you. And also the camera view transformations are applied and are supplied to you again as a Shader Lab global. So here we have float 4x4 unity matrix underscore V. Excuse me. So that is those transforms I mentioned here, getting the camera to be in the right position as applied to your objects gets given to you as that matrix there. And that matrix can be then multiplied with your object to world to create object to world view. And then the final combined version of this is the model view projection matrix, MVP. So this is the steps that we covered way back here. Modeling, viewing, and projection. So going back down again, that is combined together for you as the model view projection matrix. And you see, now, in the demos, this is the thing that annoys me slightly about Unity. Every freaking year, they decide to change this. I like this setup because it's obvious. Makes sense. You see the matrix is applied to the input position, you multiply it, you've got the output, it's clear, you've got the theory in your head, you know what's going on. They now have, and it does it automatically, the Unity object to clip position function. And so all my demos that have that, once you load them up in 2017, show this. But what's happening is this. So I'm going to have to sort that out, but there is a quick fix for this. There's a little setting you can put into the setup so that it doesn't do that pre-processing. The updates aren't performed on the shaders and they run in the old mode because there's no difference. Because what that does, if you go back to that diagram I had earlier, he says here, clip space. See, once you project, which we'll get to next week, you're in clip space where you're going to clip things against the view volume. And that means, as we sally forth onto that page there, that's what you can see, that the statement suits the function. Take the object from object space and put it into clip space. It's the same as this. Does it automatically, and it changes it every year. They just keep changing this and do these updates. I'm not sure why they do this. Maybe this abstracts it out for OpenGL and DirectX 11 and they're able to do some stuff to suit the different orderings and row column setup. Maybe because they've got a programmable pipeline and they went, oh shit, we can't just expose that as per usual. If we're going to be cross-platform, we need to use an abstract function. I don't know. Anyway, it's pretty straightforward. The key thing is, if you do it this way, and if you turn off the updates, and you can then start playing around with these things in the Unity environment in Vertex Shader. We'll talk about this in the practical session. Now, last but not least, I'm just going to create a third-person camera with a drop-in character. This video is old, but still useful. You get to hear me speak. But I'm just going to now actually run through setting it up using the standard setup. But the key thing about this is not about setting up third-person cameras. Third-person cameras. You should be able to do that from all the games you've built up until this point. Key thing is I want to show you how you just apply an abstract shader or another shader to the surface, and then hopefully for these characters the penny drops that you can download something that's all rigged and animated, and then you can just drop a material on it and make it change and use your own shaders on the surface. You probably don't want to do that, but maybe you do. Maybe you want to just add a certain Phong shading model that you've seen, or Cook Torrents, Radiance models, all those sort of things. So let's let the journey begin. No, I'm not going to have that AR Masters meeting. So let's create a new project. Let's call it Lecture 2 Third Person Cam, because we can. Alright, let's create a project. So this is just the standard Unity objects that you can get. And there we go. So for reference, what am I using? I'm using that's what I want. Oh, stop it. Oh, that's right. So I'm using my 2002 version 2 here on my Mac. Still holds as far as I can see. I actually practiced this on my machine at home. So let's import a package. Let's get the characters. Shazam! We let them there importing assets dialog go. It's frozen. Come on. I know you're a Mac. I know you can do it. Come on. Just because you're videotaping the entire scene doesn't mean it should take that amount of time. Come on. You can do it. You can do it. Yeah. Excellent. So let's just build a terrain because we don't want to fall eternally to hell. Fire and damnation of God's wrath in the coming Holocaust. No, we don't want that. We actually just want our character to walk on this surface here. So, characters, yeah, we're on third person, and prefabs. And let's just do this one here. Let's make it this size, and then the wonders of modern science, I believe. Oh, it's funny, I create a new, no, it hasn't created it. Yeah. Get over yourself. Alright. Slight delay here, ladies and gentlemen. Camera! Thank you. Alright, so at this moment in time we put that there, and lo and behold, we've got our figure moving around in front of us. So, of course, save it. Camera. So it's all pretty straightforward. Here's our third person. Always cyberpunk. Why do they always choose cyberpunk for this one? I don't know. Alrighty, so let's put the camera under the third person there, and then we'll just end up with a dodgy camera. That should just do us for the moment. It'll follow us around because the camera is inheriting the transform from the third person controller. It's all very good. And we should put a directional light in there. Let's put a directional light in there. That should work quite well now. Let's see if the camera thinks it's going to be. Yeah, great. Cool. Damn, I'm good. Look at that. Anyway, but I don't like grey, and I don't like the setup there, so I'm going to go back here, and I'm going to create my own material. So I'm in material. This is just third. We'll just call it third person because that's what I'm going to do. And then we're going to create a shader. Let's just stuff we'll put an only shader in there. Third person. This will look really bad. Really, really bad. So just drop the shader onto the material, and then turn it right over, drop it on the material, and then now that we turned it off, drop it onto there, and we can see it's on there. Isn't that awful? But we've created a custom shader and dropped it onto the surface there. So if I run that, it should be a bright white with dark sunglasses. So yeah, that's the way it's working. Now, I'm going to go very sneakily. A plan so cunning, you could put a tie on it and call it a lawyer. So we go over there, I'm going to race through the Unity demos, and I'm going to grab a simple lighting. There it is. So there. And in there, there's a Fong shader. So Fong Bui Tong, the originator of this lighting model. And I'm just so awesomely talented, I'm just going to drop it in there. So that's a Fong shader. Great. Lo and behold, I'm just going to drop it onto that. Look at that. Suddenly turn blue. And if we play with this, we'll find that I've just taken a Fong shader and put it onto there. Now, I had to play around with this, I believe, the last time I was stuffing around with it. So I've got that there. Let's highlight the camera. Let's get the inspector up. Let's look at the material. So we see that we've, remember those properties in the shaders? There they are. I've exposed the entire lot here just to stuff around with things. And what we want to do is probably make the specular power about 10. I had to do a few things with this here, that's right. And then I made the light specular into white, like that. And then I made material specular into white like that. And lo and behold, this is just to make it look like your classic sort of namby-pamby, plasticky animation. Kids, you don't know how lucky you were, because when I saw computer graphics as a child, this is all I had, Phong shading and no textures. So just to show, to sort of round off the lecture, that's creating a third-person character, and which you need for the assignment, and that's just how you add your own material to it. And so I created a new material. I then just got a custom shader, or a shader from my demo set, and dropped it on the material, and dropped the material on the character, and lo and behold, our fine cyberpunk friend looks like a heavily Phong shaded plastic man. So that should help you with performing your third assignment. Some of you will just twig this, but that's how you do it. Just drop the material on there so you can put the custom normal mapping shader on there. I don't want to see any usage of any of these standard shaders. It's just going to be your shader, your normal mapping shader on the surface of whatever character you pick. Up to you. Grab whatever you want, or you can use that. It doesn't bother me, but you've got to get the normal mapping shader to work. So I'll just pull out of that. Bye-bye Unity. I do that in this video here, but it's an older version, even older than 2017 version 2. So there'll be some differences. And that's the end of the lecture. Thank you very much.